So welcome everybody to this Cambridge Zero Research Symposium on mitigation. I'm Lata Sahonta. I'm from the university's Energy Interdisciplinary Research Centre, and I'm chairing the symposium today. We've got 3 keynote speakers and 3 early career researchers. So we've got James Woodcock, Ian Parry, Jonathan Cullen, and then our early career speakers are Alan Bowman, Emily Bugden, and Christos Vlachakis. For those in the audience, please keep your microphone muted except when you're invited to ask a question. And it's quite nice for the speakers to be able to see your faces when you're asking questions. So do keep your camera switched on if you want. The way to ask questions is to submit them into the Zoom chat, or at the end you can raise your hand virtually using the Zoom function. And if we run out of time, can we request the speakers to perhaps give some written answers in the chat? And for those of you, if this is your research field, please do chime in with your own comments and answers in the chat as well, if you feel that will add to the discussion. This session is being recorded and you can watch it again on the Cambridge Zero YouTube channel as well. Just to let you know that this is actually one of a series of symposia this term. We've got coming up next week a symposium on nature and biodiversity, and then after that we've got one on AI and sustainability, hard to abate sectors, and working globally, which is in December. If you are an early career speaker and you'd like to present at one of these symposia, if they fit into your research field, then you can have a look at how to apply to present on the Cambridge Zero website. You can also register for other symposia and have a look at lots of different activities that Cambridge Zero is doing for COP26 as well. Quite useful way of keeping abreast of all of the different things happening within Cambridge Zero is by getting onto our mailing list, and you can have a look at our social media as well. So follow us on Twitter too. Okay, I'm just going to unshare my screen, and then we can have our first keynote speaker, who's James Woodcock. James leads the Public Health Modelling Group at the MRC Epidemiology Unit, and James develops models to help understand the health impacts of changes to how we travel. His talk is entitled Moving to Zero Carbon Transport. So James, please go for it.
Thanks, Lana. Okay, is that working?
Looks good.
Great. Okay. So, what's happening in terms of transport? Why is it not moving? Yeah. Over the last 30 years, we've seen big reductions in the UK greenhouse gas emissions in the energy sector, and some smaller reductions in other sectors too. But transport has remained stubbornly high and is now the sector with the biggest contribution to greenhouse gas emissions from the UK. When we look at road transport specifically, and again looking back to 1990 and then now on to projections on to 2050, when we should be getting to zero carbon, what we see is that on the DfT's current policies, all the things that they've got lined up at the moment, we are a long way from getting there. There is a big gap. Emissions, yes, are expected to fall, but we need very rapid emission reductions in the next few years and then continually until 2050. Road transport is a problem. There's possibly even bigger problems though with things like with aviation. I mean, this is looking at 1990 and 2019. Cars and taxis, very small fall, more than offset by the increase in vans, delivery vehicles and so on. But aviation, what we've seen is going up from 16 megatons of CO2 equivalent to 37. So a very large increase. And at the moment, aviation hasn't traditionally, or international aviation hasn't been included within the UK's kind of domestic emission reductions. However, this is supposed to change. The UK does have some policy ambition. I mean, this is not from things that they're saying right at the moment, but from back in May. UK government set in law world's most ambitious climate change target, cutting emissions 78% by 2035 compared with 1990. The sixth carbon budget will include the UK's share of international aviation and shipping, which is obviously absolutely vital. And they claim that this will bring the UK more than 3/4 of the way to getting to net zero by 2050. So, you know, some positive words there, but at the same time, much as we see this policy ambition, we also see a policy contradiction. The first one I'm just going to highlight here is from the recent mini budget, the lowering of domestic air duty. Now, obviously, all the politicians and important people are flying up on private jets to Glasgow, and when you look at what emissions are travelling between Glasgow and London, you see that obviously emissions are far higher than they are by plane, than by cars, and much higher than by trains, electric cars, or coaches. So particularly including for aviation the indirect emissions, which increase things further, you see that flying is a very unsustainable option, and clearly one that could be avoided for domestic flights with what's a kind of 4-hour train journey between London and Glasgow. I mean, it is important to also think about who is responsible for these emissions, and flying in particular is very, very highly skewed, with 20% of households doing over 3/4 of all flights, 10% doing over half, and 1% doing around 10% of all the flights. There are a lot of people who do not fly, certainly in a given year. Obviously ignoring the last 18 months when many of us have been flying a lot less, but a lot of people in previous years do not fly in a typical year. Another area where the UK has some good ambitions is around cleaner vehicles, and it's good. Most countries have not done this yet, but the UK has set an end date for the sale of conventional vehicles and for hybrids. Hybrids have only potentially only, well, the benefits vary, but they're not always that large. So these dates are not that far away. But unfortunately, there's no date set on use yet. And I mean, vehicles that are sold in 2030 or hybrids in 2034, they're going to still be around after some of them after 2050. So plans will need to be done to speed up the transition. And here we're often seeing cities taking the lead on use. See, cities can't control sales, but they can control use. And we see here the ultra emission zone just come in London. I mean, there's pros and cons to this, and I mean, these kinds of pricing mechanisms, but progressively these are ways which the use of polluting vehicles can be reduced at least from urban areas. So some positive movement. However, at the same time, there's another contradiction, that probably the easiest way to push people beyond stopping the sale is the fuel duty escalator, which hasn't been abolished but has been frozen for the last 12 years. And I mean, this makes their own estimates here are nearly £2,000 a year, and this obviously makes a big difference to the sense of for an individual making a switch over to electric vehicles or just reducing car use. Another area of contradiction is the road building policy. 28 billion investment for England's strategic road network between 2020 and 25. And recent estimates were that this could remove around 80%, so the vast majority of the CO2 reductions planned during that time period due to increased, due to the construction of the infrastructure, due to faster speeds on the network, and due to induced demand. Building more roads leads to an increase in car use. It makes it faster and easier to get around by car. So to me, the plan seems to be business as usual, largely with cleaner cars and planes. And the problem is that rising use largely offsets efficiency gains. Electric vehicles take more energy to produce, and the greenhouse gas emissions depend, of course, on the energy source. And there are competing demands on clean energy. So the more we need for transport, then the more that's competing with the demands we need for heating and so on. And these policies together are too little, too late. And they also don't consider the other harms of transport, which is where I do a lot of my research. So I'm now going to just say a little bit around transport and health, particularly around electric cars. Now, obviously, electric cars remove tailpipe emissions, and that's important. There can still be emissions of some of those gases from, of course, the power stations if the electricity has been generated by coal or by gas. So you can still see particulates and other pollutants generated in the life cycle, but they're not there from the tailpipe. However, already when we're thinking about PM2.5, then the fine particulate matter, then the majority of that already is coming from brake and tyre wear and resuspension of road dust. So it's not actually the majority is coming from tailpipe emissions. I mean, there's other pollutants from tailpipe too, of course. And the greater weight of electric vehicles can increase this. Now, there are things to be done about that. It's not an unsolvable problem. There are measures in terms of regenerative braking, low emission discs and pads, but all of these need to happen. That they are not automatic benefits that we will just see with electric cars, or at least very slowly with electric cars. And certainly we find that emissions do not go down as fast as people think with the move away from conventionally fueled vehicles. Another area of health consideration is noise pollution. And noise is often not considered as serious as air pollution, but increases risks of heart disease, stroke, obesity, and diabetes. And some studies that have compared the burdens of air pollution and noise have found they're actually quite similar in places like Madrid, diverse places, Madrid, Houston, and Warsaw. So it's a big issue, noise pollution, and the harms it has. Now, electric vehicles, obviously the engines are potentially quieter, but when they have to make some noise, but when you're, for safety reasons, but when you're going faster, most of the noise is to do with the road surface contact, and they don't reduce that. So noise is still, and there's been far more attention paid to air pollution, and therefore, it's getting more things done about it. So, noise is something we need to be much more mindful of. One thing, of course, electric vehicles don't do is they don't give you physical activity. And a lot of the work that we do in the MSc Epidemiology unit is around physical activity and the health gains of physical activity. And this is from a major dose response meta-analysis that we have done. And this is expressed in terms of the relative risk of all-cause mortality. We looked at many different diseases, but this is the most evidence for all-cause mortality. And the exposure is in marginal met-hours per week, which is a measure. It recognizes the different intensity of different activities, combines them together based on their duration. To make it easier to understand, this here is about five marginal met-hours per week. It's around 2 hours walking per week. And for this, you are seeing a substantial reduction in the relative risk of all-cause mortality. And then the curve is non-linear. So at higher exposures of physical activity, say 3 hours of cycling, you would see incremental gains, but they're not as large at this place in the curve as they are for those who are doing the least activity. We've looked at we've done studies also looking at the potential of cycling for health and for climate. This is available in the DFT funded propensity cycle tool, and also in the impacts of cycling tool. I don't have time to explain the differences fully, but using the impacts of cycling tool, we said if everyone was as likely to cycle a trip, allowing for the distance, then as existing cyclists, that is people who cycled in the last week, and the trip stayed the same distance-wise, then in terms of physical activity, you could see huge gains in population health with around a 10% reduction in all-cause mortality, and modest but important reductions in car distance. We didn't have a full emissions model, and these would be bigger if you had e-bikes, electric assist bikes, because people would be willing to go a bit further and place slightly longer car trips than they would with a conventional bike. So that's one way to look at it. But there is more optimism in terms of the emission reductions from a study recently by the PASTA project, Christian Brand, here looking at life cycle assessment, so more integrated and multiple European cities. And here they're comparing a more narrow definition of cyclists, people who cycle every day, and they are not assuming that they are looking at the actual trips they make, not assuming trip for trip substitution, and they found they had up to kind of around 84% lower emissions from daily travel than non-cyclists. Now, I think if we increase cycling, the reality is going to be somewhere in between, I think, and we're doing some more work that will help with this in the future. There's also a lot of other health impacts to consider as well from transport. A recent review by Gleisner et al. Looking at transport mode, its associated infrastructures, technologies and land use, found it affects health through multiple pathways. Obviously, traffic injuries is the most obvious one I haven't considered, but there's many others, including green space, mobility independence, contaminants, social exclusion, urban heat islands, community severance, and so on. So there's a lot to consider here and think about when thinking about how changes to transport could impact on health. It's also important to think about health inequalities and social inequalities. And when thinking about transport here, we need to think about what people are exposed to, like air pollution and green space. We need to think about the location choices and travel distances to work and study and the housing market. So we need to think about the kind of work people have. I've been able to work at home during the pandemic. The people here in the tube were not able to. Of course, around resilience and underlying health status, potential issues around, particularly for women, violence and harassment when traveling, cost affordability, and the responsibility for harms with small numbers of people responsible for large proportions of emissions, and some people from the richest areas responsible for disproportionate amounts of air pollution, which is experienced much higher by people in lower income areas. Now, we know about the principles for reducing car use. These include density, denser cities, high population density, distance, reducing distance to destinations, diversity in terms of the land use, desirability in terms of the pleasantness of features, design in terms of infrastructure, quality infrastructure, making short and direct routes for walking and cycling, longer for cars, pricing, of course, parking restriction, and public transport. A lot of these things have come together in the visions that people have been putting forward around 15 or 20-minute cities, with a quote here about to do the 6 main activities of living, by Professor Carlos Moreno, advising the mayor of Paris. And again,
got a minute left, James.
Yeah, fine, only a couple more slides. And another positive policy, to come back to the positive things that we have seen in the UK, supported nationally but implemented locally, is around the low traffic neighbourhoods. And here we have seen, based on some preliminary results, around big reductions in car ownership in a relatively short period of time, increases in active travel that are quite substantial, reductions in car use, substantial, and also reductions in traffic collisions, crime, and no increases in emergency vehicle response time. So positive changes from the low traffic neighbourhoods. And just on the kind of couple of slides, achieving sustainable transport. Electric vehicles are necessary, but they're not sufficient. More walking and cycling is good, but it's not sufficient on its own. We need to reduce travel distances to make things nearer. We need to restrict car use. It needs to be made more difficult. Car ownership needs to fall, thinking about mobility as a service. And rather than one size fits all, the family car, we need to think about different vehicles and for different purposes, which works with moving away from ownership, from individual ownership. We also need to do some about flying, and particularly frequent flyers, and the airport expansion. And last but not least, reducing transport inequalities. However, I would say that UK policy, there's some good elements, but it's contradictory and it's insufficient. I would say a lot of this comes from competing pressures, but maybe some of it also comes because they don't really expect us to succeed. And when you've got Johnson's quote here, when asked about climate change, and he starts talking about the Roman Empire and about uncontrolled immigration, then what I hear here is that he is not serious about averting catastrophic climate change. But what he is saying is that we will not particularly try and stop the climate change, but what we will do is put barriers up to some of the most vulnerable people who are escaping from the catastrophic effects of climate change. Thank you.
Thanks very much, James. Please do put questions for James into the chat. We've got a question from Shafiq here. How will the government replace tax revenue from loss of fuel duty?
Yeah, good point. I mean, everyone says that they're going to have to introduce road user pricing. Yeah, but obviously they are reluctant to do so. And the sooner they started moving towards that, the better, because it's going to be it'll be an increasing problem. But at the moment, electric vehicles, they escape most of the taxes and so on, which, I understand there's a move to try and get people to use them, but there will definitely need to be another form of pricing instead.
We've got another question from Eric. We know how to encourage bike use and active travel, but it's not being implemented at nearly the right scale required in the UK. How can we change this? And is this a role for local government? Can we follow examples from countries like the Netherlands where it's been more successful?
Yeah, and I think, certainly in terms of our cycling design standards, which now nationally are pretty good, and a lot of that is taken from the Netherlands. I think there's an awful lot we can take from that. I think local government, certainly in terms of, I'll answer I can see the next questions too. Local government has a big role in making more livable, more attractive places. Whether it's possible to do this at the kind of scale and speed we need for greenhouse gas emission reductions is a different question, because there we don't just need a few areas, we need everywhere to do this, and as rapidly as possible. And the Netherlands is great in terms of cycling, but I would say they drive too much. You can't just kind of say, oh, it's great, there's lots of cycling. From a health perspective, okay, fine, and the safety record is great, but and it makes the cities nice places, but people you drive all around the kind of Randstad connected city network, and they need to reduce that. So the same time as promoting active travel, that's why I think low traffic neighborhoods are particularly good, because they do positively restrict cars as well. While just building a nice new cycle track, you may still get a lot of car use. These studies of the low traffic neighborhoods have tried, just looking at the next question, have tried to look at reductions in traffic as a totality and the impact on major roads. And from the data so far, there does not seem to be a general increase. Obviously, there's variation, and it's hard to tell and hard to make controls properly. General increase in traffic on other major roads, but more research is needed, and I'll soon hear if I've got some more funding to look at that. I mean, yeah, self-driven vehicles. I mean, I didn't have time to go into that. I mean, but yes, I mean, there is a real risk that further increases driving. And I mean, some people in the US been working with, recently looked at, the health impacts of autonomous vehicles, big reductions in injuries, big health gains, but still, compared to active travel scenarios, much smaller health gains. But yeah, I mean, that there is a real risk that AVs allow motorization to keep on increasing, because you can send your car going around while you're waiting for it and things, while you're doing something else.
Okay, thanks very much, James. If I move on to our next keynote speaker, it's Professor Ian Parry from the Institute of Astronomy. Ian's research focuses on unfolding space telescopes and using total internal reflection telescopes to study climate change. And his talk is called High Resolution Thermal Infrared Space Telescopes for Climate Change Mitigation. So Ian, if you would like to share your slides.
Yeah. Is that working?
Looks good.
Okay, thanks, Lathan. I'm an astronomer. I'm not a climate change expert at all. This is my first ever talk at a meeting about climate change. So please, everyone, be gentle with me. I'm going to talk about technology. My expertise is in the technology, really, not in the climate change part. But it turns out that this telescope technology that we're developing has great potential for helping mitigate climate change. And so the funding I'm getting at the moment is coming from that aspect, not from astronomy. So yes, my title of my talk is High Resolution Thermal Infrared Space Telescopes for Climate Change Mitigation. Thermal infrared is basically from about 8 microns to 12 or 13 microns wavelength. And what it's doing is, so those of you who may be familiar with handheld thermal infrared cameras, basically you see the heat, you see that they basically give you a measure of the temperature of the surfaces that are in the field of view. And so we're basically planning to put those same cameras in space with a decent telescope on the front so that they still have a good resolution. Okay. Oops. Right. So the main aim of this project that we've received funding for through the UK Space Agency is to develop technology to help tackle climate change. They had a call was specifically to address that problem. So we've had money in 2 lots. We had money to fund activity between November 2020 and March 21. And then we had a pause, and then we were able to get more money from them, and we're currently running in another 6-month project, which started last month and will finish in March, which is just a continuation of the first one. It's just a strange way the UK Space Agency do their funding. So that particular project is specifically for tackling, for basically verifying what energy is being used in buildings. It's not every single way in which energy is being used. We're mainly looking at, we're only looking at buildings in terms of that project. But potentially thermal infrared telescopes can measure the energy use of pretty much all the buildings on the planet. And if you have enough telescopes, you can measure that on a daily basis. So specifically, we're talking about a telescope design that gives us about 6 meters per pixel in the pictures. And if you have something like 5 or 10, that will give you most buildings or on a sort of reasonable time scale. You want very almost continuous time scales, then you might push this constellation up to about 50 satellites and then really keep an eye on everything. certainly at this resolution, the biggest CO2 emitters will be identified. And the whole idea is if you can identify, you can prompt some sort of remedial action. This is potentially high impact because 28% of global CO2 emissions come from the thermal management of buildings, either heating them or cooling them. And the enormously high ones will be easily identified, and of course they're the ones that actually contribute mostly to this 28%. Okay, so that's specifically what we got funding for. But I just wanted to make a point that actually in general, this technology can potentially be used to map nearly all the carbon emission fuel consumption on the planet, because basically whenever you burn anything to produce heat, that will be visible from these telescopes, because whatever that process is happening inside, it will make the outside of that building or factory or vessel or whatever get warmer, and you'll be able to tell that there is some energy production going on inside something. So unless you've got unless you're burning fossil fuel deep inside a mountain or maybe in a submarine, it's going to be visible. I mean, I don't know what percentage of the fossil fuel will be visible, but it must be something like 99% or something like that. So you can't hide from this technology. And of course, the carbon emissions are generated in lots of different ways: power stations, planes, ships, lorries, etc., etc., steel production, cement production. So potentially, it's a great way of monitoring what's going on. Okay, but then you might say, well, but we know what's going on. We all know what we're burning. We all know what energy we're using. Why do we need to watch it from space? Well, it's because countries and companies and even individuals will have to sign up to agreements. There will be, I'm sure, legislation introduced to discourage bad practice, and there will be incentives offered to encourage good practice. So there'll be sticks and carrots, and basically, to prove that you're doing the right thing, people will have to make reports on their activities, and that's why you need verification. It's a bit like speed cameras. We all have speedometers in our cars. That doesn't mean that we all obey the speeding limits. So you need speed cameras to hold some people to account. So at the moment we're developing the technology. We don't have these things in space yet, but to learn how the images tell us useful things, we're flying a drone around Cambridge with a thermal infrared camera on it to see what kind of insights we can get from the data. So this picture here is a picture of the Institute of Astronomy, where I'm based, and you can see the blue part down here. So let me just say something basic about these images. The sort of white and yellow and orange parts are the hot parts, and then as it gets cooler, you move to this blue color. So you can see here a roof which is relatively cool. This is a modern building, and over here in this corner in the top right, you can see an old building. This is a very old building which is listed. It's over 150 years old. It's the old observatory building, and you can see the facades of this building are quite warm. So you can see straight away where the heat is being released from these buildings. And this one, so the fuel consumption for this building is higher than for this more modern one here. And you can also see things like this white dot here. This is an air conditioning unit, so it doesn't just pick up heat, it also picks up the heat that's being pumped out through air conditioning units. This data has a resolution of about 27 centimeters per pixel. So what we actually do is we fly these drones on a raster pattern over big areas, capture the data at what is quite high resolution, and then we stitch the images together and downgrade the resolution to 6 meters to emulate what we would get from a satellite. Here's another example of some data where we're overlaying. So this is the Center for Mathematical Sciences, and we're overlaying the thermal infrared images into this surrounding Google normal image. And then over here, you see it downgraded to about 6 meters resolution. And so for large buildings like this, you can still get quite pretty good data on energy use within the building. Okay. All right, now I'm going to say something about the technology. This is actually the bit where I actually know what I'm talking about. So the technology we're developing is an unfolding telescope. And so it's the CubeSat. So this is the picture here in the top right shows the size of the satellite in its launch configuration. It's only 22 centimeters across, about 30 centimeters from top to bottom. And so that's a relatively low-cost thing to launch. But when it gets into space, it unfolds into this much larger telescope, and that's what makes the telescope have much higher definition. This unfolding makes it 3 or 4 times better in terms of the definition in the images. So potentially that means you can have a lot of these. You do need a lot of them to globally monitor what's going on. And that makes a big difference to the cost and makes it much more viable as a constellation. So that's part of the project, was to develop this technology. I'll say something about that in a minute. We also looked at how the data can be used to understand the energy consumption in individual buildings. In particular, we want to understand the effects of the resolution of our images, what the local weather was at the time when we took the image, what the viewing angle is, how that affects the insights and so on. And another part of this was to talk to stakeholders, potential stakeholders for this data, to understand what they actually want. So they could be, for example, energy certificate companies, or companies that have a large amount of infrastructure and they want to monitor it to make sure that they're doing the right thing and meeting their commitments. And then finally, the last part of the project was just to make sure that the telescope they were developing is compatible with the rest of the satellite, because obviously the rest of the satellite has to have things like power and communications and attitude control and so on. So there was a lot of general satellite stuff that we needed to consider and make sure that it all fitted together to make a working satellite. So here's a prototype that we built. So this is an actual model of that thing I just showed in the previous slide. This is it in its folded up configuration. Here it is with the mirrors of the mirror folded out. Here it is with the secondary mirror extended out. And so you can see there it's unfolded so it's unfolded to become a fully sized telescope. This didn't work optically. This was simply to prove the mechanics of the unfolding scheme. Check on the optics, which is a much more difficult problem. We had a separate prototype in the lab. This is a more difficult problem because these mirrors, so in this one here, let me go back, in practice, these mirrors have to be positioned to a fraction of a wavelength. So they have to be positioned to about a micron or so, which is that's 1/100th of the width of a human hair. So if you just unfold them, it won't work. You have to do something clever to get them aligned at that very high accuracy. So that's what this model here was, this lab setup was aimed to do. So my student who's just finished his PhD, George Hawker, was working on this. So he had a 3 mirror system in this case, and he had a metrology system that would actually measure the position of these things with very high accuracy. And then all of these things have got actuators on them. So once you measure them, you can then work out how wrong they are, and you can tweak up the positions of these things to make them correct. And so he was able to close the loop on this and make this thing work as a telescope. Here's a picture of somebody who was outside the lab waving at the time. This was about 30 meters away, this person. That worked extremely well. So we were able to prove that we know how to do this self-aligning. Okay, so there's just again a picture of the actual thing that we're trying to make.
You've got 1 minute, Ian.
Okay, right. It's gone much faster than I thought. Let's skip. So one of the things we did was try to get it to try to correlate the actual temperatures we're seeing in the images with known energy consumption values. This is preliminary data. As you can see from this, we've still got quite a long way to go. We were not able to really produce a very strong correlation between what we were seeing and the known energy use. Clearly, we need to add in extra data to get that correlation to work better. I'll skip through that. Well, the last slides here were mainly just summaries of what I've just said anyway. And this slide here was just to say something about the all the other stuff inside the satellite that is necessary to make it work. And yeah, we basically demonstrated that looks quite feasible, and we're on the right track. So yeah, well, actually, I think I can just stop there. Yeah, that's the end of my talk. Yeah.
Great, thank you, Ian. We've got a couple of questions in the chat. One from Shafiq: how are space telescopes regulated internationally? Are there any privacy or security considerations?
Yeah, that's a really good question. Privacy, no. That's one of the, either depends how you look at it. That's a huge advantage of them, or a very scary thing about them. So in terms of climate change, I think it's a good thing, because it means that you can check up on anyone. I'm not going to name any particular countries or anything, but it means that as the UK could basically go to another country and say, you've signed up to this, but our data tells us that you're not doing that. And there is no law that says we can't do that. It could work the other way, of course. They might come to us and say, we're not doing our part either. Sorry, privacy, the security, again, no, there isn't anything that says, I mean, yeah. I think there may be some agreements about things that are specifically military, but yeah, generally speaking, there's nothing. Okay,
great. There are, I think, a couple more questions in the chat, so if you don't mind just giving written answers to those. Thanks very much, Ian. If you unshare your screen, we can move on to the next speaker, who is Jonathan Cullen from the Department of Engineering. Jonathan's research seeks to understand material and energy flows required to support energy, transport, buildings and infrastructure systems. And his talk title is Demand Reduction, the Missing Mitigation Strategy. So Jonathan, thank you.
Thank you all. Can you all see my screen okay there?
Yeah.
Good. So I'm Jonathan Cullen from the Engineering Department. I run a group called the Resource Efficiency Collective, which is about 20 people now, PhDs and postdocs working on this problem of how we can deliver future energy and material services while at the same time reducing resource use and environmental impact. And we focus a lot on demand reduction in our area of research. And interesting to note that the two talks so far have actually focused on demand reduction quite a lot, which is really exciting to hear. So thanks, James and Ian, for that. Just an example of one of the projects I'm running, which is a project on the global petrochemical supply chain. So that's fertilizers and plastics, and international project. And we're really interested in mapping the whole supply chain so we can understand demand reduction things you can do, recycling, stopping single-use plastics, alongside making an ammonia plant more efficient, for instance, or carbon capture and storage. So really being able to see all the options for mitigation. I want to start with this picture here, which I did for my PhD a while back now, so apologies, the numbers are quite old. But it's a global picture of how energy is used, transferring energy from fossil fuels, mainly on the left side, with the emissions shown in red, through the electricity system, through a whole lot of devices which convert energy into more useful forms. Blue is kind of motion or kinetic energy, red is thermal energy, heat, black is some other stuff we create. The kind of purpley color there is the materials we make. And tracing that energy use, or allocating it all the way through to the final services that we actually use it for, because in the end, no one actually wants oil or gas or a solar panel. They want sustenance, hygiene, thermal comfort. And we generally think about the supply side being this front end here, getting kind of fuels out of the ground, or perhaps nuclear energy and renewables down the bottom, and converting it into electricity or into refined fuels. But there's also this other whole side up here called the demand side, which includes all the devices like cars and trucks and planes and furnaces and hot water systems that we use to convert this energy into useful forms for us, and all the material processing that we do. And the main space I focus in my research is on this demand side, which is very exciting. I just wanted to highlight this paper, which really pushed me towards demand side when I read it. And it's talking about how end-use technologies or demand-side technologies are kind of marginalized for climate change innovation. I'll just read from this. We find efficient end-use technologies contribute large potential emissions reductions and provide high social returns on investment than energy supply technologies, yet public institutions, policies, and financial resources pervasively privilege energy supply technologies. And it's not hard to look around even the research in Cambridge and see that evident, apart from the two speakers that have just gone, which is great to see. And this is just a snapshot. They reviewed a lot of innovation metrics or indices, standard ones and some new ones. So these are all lists of different indices that they reviewed. A whole lot of them are on the inputs to the innovation system. So, what knowledge, what institutions, trying to measure what goes in, and you can see the brown is on supply side and the green is on demand side. So most of our money in innovation goes into supply side options. A fact that about 90% of the America's R&D money has gone into nuclear energy over the last kind of 50, 60 years. But when we look at the outputs, what we actually get out, and we try and measure the outputs of innovation system, we find that you get a lot more mitigation, you get a lot more effect and social benefit from the demand side options and working on them. And now, just looking now at scenarios, this is work from IPCC. I'm a lead author on industrial chapter for that, and these are pathways to 1.5 degrees Celsius. And you'll see that normally we go for if we're thinking in a supply side conventional wisdom, we go for P3 or P4. So these are options where we are relying heavily on BECCS, taking carbon out of the atmosphere, CCS type arrangements, where we're having to go negative out in the second half of the century to kind of cover the emissions we've made in the first half. And there's quite a lot of groupthink around those types of options, and the scenarios have better data, so we produce a lot of scenarios in that space. But there's some emerging scenarios coming through. On the left-hand side, P1, this is a low energy demand scenario, where we could get there without relying on perhaps these slightly risky and difficult and expensive technologies by reducing demand. And so for the rest of the talk, I really want to focus on this paper. It's a paper I'm an author on, written from the IASA team in Vienna. So quite a big team of people that they did a low energy demand scenario for meeting 1.5 degrees. This is now adopted in the IPCC kind of group of scenarios. And what it aimed to do that without negative emission technologies, so without CCS, and try to look at focusing first on lowering energy demand before we looked at cleaning up CO2 emissions. So I want to go through that. The scenario has high levels of energy service, so providing people what they need, decent standard of living, so it looks at both global south, global north, and making sure the global south is catching up in terms of service delivery. Very low energy demand, so 250 exajoules, and I'll come to that later. That's about what we use now. Lots of efficiency, electrification involved in it, and it stays below 1.5 degrees without these negative emissions and delivers on a lot of sustainable development goals. New trends, it takes advantage of these new trends such as changing consumer preferences. So we're seeing changes in diet towards vegetarianism, away from meat, change in materialism. So people using a service rather than owning things. We're seeing that with younger people with transport a lot. New business models around circular economy and materials, pervasive digitalization and ICT convergence, and rapid innovation in granular technologies. And also I'll go through these and explain how these are used in the scenario. Just as a snapshot, these graphs here show for different parts of the economy, thermal comfort, mobility, consumer goods, what is changing. Now the blue shows that the level of service provided goes up. So we are providing more mobility, but we're doing it at a much lower intensity. And that results in a reduced amount of final energy demand. And when I talk about intensity, I'm talking about energy intensity, not carbon intensity really. So even though we're providing more service for people, we are seeing a reduction in overall final energy, or a relative reduction across these sectors that are modeled. What type of technologies are we talking about? Well, we know passive house specification for buildings allows us to get to very, very low energy inputs by insulating very well and interchanging air, producing leaks, growing very fast, and as proven technology needs adoption. I brought up this example a little bit in jest, but this is the most efficient car that's been designed and does 15,000 miles to the gallon, which is much more than a normal 30 miles to the gallon. It's hydrogen, and it weighs 30 kilograms. Now, not the type of car that you can put your golf clubs in the back of course, but it gives you a kind of an idea of how far we could go in technologies and really reducing the demand for energy for transport. And perhaps more realistic is just thinking about the size of our vehicles. This is a Mini back in the 60s, and this is the current Mini, and you can fit the old Mini inside the new Mini. So a lot more materials, and moving around materials uses lots of energy and emissions. Nice quote there from Jeremy Clarkson, which is very relevant, I think, to James's talk about jogging. On ICT, there's a lot of convergence work that was done in this paper. So what we're trying to say is you could have lots and lots of devices in your house that use lots of energy, have lots of embodied energy, standby energy on the right, that's those graphs, or perhaps you could use one iPhone, which has much lower energy and much lower embodied energy. So this idea of doing multiple tasks with one device potentially could save us a lot of equipment, material, and energy as well. In reality, we tend to just buy more devices, but I think there's a behavior change there. And Julian and I wrote a book on sustainable materials without the hot air, and that's with the modeling that I submitted into this paper. So on materials, I've just picked out actually these scenarios from the International Energy Agency data showing the effect of material efficiency. So this is kind of material demand on the left in their normal scenario, and on the right in their sustainable development scenario. And in between, there's, for steel and cement, these reductions in use of materials by designing things better, by decreasing the amount of use, etc., and balancing that out. And this is IEA, they're quite conservative, but we're getting big chunks of material savings. by reducing demand for materials. The other thing that we noticed is this tendency to go from large, lumpy units, large size, high unit cost, high risk. You know, the big example being a large nuclear power plant, which takes 30 years to make, and you get one chance to make it right. The learning and kind of innovation there is very hard to make work. You have a new plant every 5 years. Whereas modular, smaller devices, you can innovate much more because you're producing a lot more units. And the economy of scale is in the manufacturing rather than the actual energy kind of delivery of the device. So that is why we've seen massive reductions in the cost of solar, the cost of wind, the cost of batteries, is mainly to do with the size and the learning that you can get very quickly in those devices, as opposed to not seeing those price reductions in large lumpy investments. So the scenario really starts from this demand side and works left. So I just wanted to present some results for you from that. So it reduces demand first, and then it looks at decarbonizing that demand second. So what we get, so this is a picture here of the kind of demand written along the top there. So this is historically increase in demand for final energy. Currently, we're at about 294. This scenario gets us down to about 245 exajoules a year. So less energy than what we're currently using today. That's very ambitious. On the right, I'm going to show you most scenarios have you up at around 450 exajoules per year. So it's really heavily going after demand reductions. But the balance between industry, non-energy, residential, commercial, transport stays roughly the same when you do this. So we're seeing demand reduction across the whole, all four sectors. When we look at the final energy demand by kind of this what fuel it is or what source has been happening, what you're seeing is a massive move towards electrification, electricity, huge reductions in fossil fuels of coal and oil, some in biomass as well. It's eliminating your stoves in the global south. So that by halving the amount of energy we need, we make it much, much easier to decarbonize that electricity. We only need half as many wind turbines, essentially, as what you would normally need. And looking at the primary energy sources for that, you know, again, you can really reduce the amount of solar, wind, nuclear that you're needing to build, which is key at the moment because we just can't build it fast enough. And we're not relying on any CCS or BECCS in this scenario. And in terms of sustainable development goals, it mainly focuses on the goal 12, responsible consumption and protection, but we also do analysis. It affects 12 of the other the goals as well. And so reducing energy, and we were hearing that a little bit earlier from James, reducing the amount of energy you use. Cycling has health benefits, it has benefits on air pollution, has all of these multiple benefits across the scene, as well as decarbonisation, so worth doing. The big caveat is people don't want to be told what to do, and Boris Johnson recently just quoted that we're not going to tell you what car to drive or whether you should eat meat. And demand reduction gets kind of associated with this telling people what to do. But I want to argue back at that and say, well, firstly, you are told to do all sorts of health and safety regulations, from the way your houses are designed, the stairways, the windows. There's lots of things we are being told what to do, and yet we seem to have an aversion to be told what to do in terms of environmental rules. Many demand reduction options involve no change to the service, so we can deliver the same service with just less energy and material. Sharing a car, for instance, might do that. We are struggling with supply side options to just decarbonize. We just can't build renewables fast enough. We just can't decarbonize with CCS fast enough. So reducing energy demand gives us a chance of reaching our goals because we don't have to build as much decarbonisation in the supply. And I think finally the real choice is not between kind of telling someone to do, but do you want to pay more tax to build CCS plants through the country, Or would you prefer to maybe drive your car less, or walk more, or share a car with your neighbor? And these are the real choices, because we will have to pay for this mitigation in some way. And sometimes it might be easier to change your behavior than to pay an extra tax to do something. And finally, you know, just one key advantage of doing demand reduction, which is overlooked, is the emission reduction happens immediately. If I plant trees, I don't get that emission reduction for 50 years. If I build a nuclear power plant, it's going to take 25 years to build it and another 10 years to pay back the carbon and the concrete. So I'm 35 years before I get any gain on emissions. If I reduce demand tomorrow, if I get rid of my car tomorrow, I instantly reduce emissions to both materials and energy. Thank you.
Okay, fantastic. Thank you, Jonathan. We've got a few questions in the chat. There's one from Keshav here. This, what is the low-hanging fruit in demand reduction, and how do we get this adopted?
Yeah, it's a good point. Unfortunately, there's lots of low-hanging fruit, I think. But I would say that, a huge challenge is to get our buildings to zero carbon. And that's got to be done with insulation, mainly, I think, and some heat pumps. So that's a massive challenge there to do, which is a demand reduction challenge. I think moving modes of transport as well. James was talking about redesigning cities. That's quite hard to do, but we can do a lot. Our cities, even Cambridge, where we're quite restrictive on cars, is fully designed around cars. Half the areas are assigned to roads. Parking is a big issue. People who bring a car into your department are subsidised £2,000 or £3,000 a year to be able to park that car there. Where if I bring a bike, I don't get £2,000 or £3,000. So there are so many ways where we're just biased towards a certain behaviour, which and subsidised to take that behaviour, where we could change that immediately. Okay,
fantastic. If you don't mind answering a few of the questions in written form in the chat, that would be great. I'd just like to thank Jonathan for this fantastic talk, and thanks so much to all of our 3 keynote speakers, to James, Ian and Jonathan, for really fascinating talks with very positive messages about the research being done into mitigation. We can move on to our early career research presentations. Our first speaker is Alan Bowman. He's working with Sam Stranks' group at Cavendish and chemical engineering on halide perovskite photovoltaics. And Alan's talk title is The Maximum Efficiency of the Next Generation of Solar Cells. So Alan, please share your slides.
Thank you very much for the introduction, Alita. And yeah, I've really enjoyed all the talks today thus far. So yeah, moving straight from the demand side to the supply side. Yeah, I'm based mostly in the physics department, and I've been working on the next generation of solar panels. To tell you about that, I first need to give a little bit of an introduction on where we're currently at with current solar panels. So yeah, I think everyone here probably knows that point already. Nearly all solar panel designs, when you really boil it down to the simplest possible model, basically look something like this, where you have this single layer of silicon, and that's absorbing all of the sun's light, all the different energies, from low energy red light to high energy blue and purple light. And you can do some relatively straightforward physical analyses of this to work out that the maximum efficiency of this kind of design is 29%. So yeah, for 100 watts per meter squared coming in, you'll get 29 watts per meter squared coming out. And we're starting to get quite close to that experimentally too. So most solar panels that you can buy today are probably about 22% efficient. In the lab, silicon solar panels are now about 26% efficient. And the other side to this that I think some of the speakers today have already touched on is solar panels don't really cost very much. So when you actually buy a solar panel, you're not paying for the solar panel, you're paying for the inverter and the electrical connection to the grid, and if you're having it on your roof, the scaffolding and everything else. So really the game today within solar is how do we push up the efficiency without pushing up the cost of solar panels very much. So how do you get more energy for roughly the same amount of money? And there's a few different ideas of how to do this. I'm just going to talk about the one that, at least at the moment, looks the most likely to be commercial in the next couple of years. So I already said this design is limited to something close to where we're already at. What we can instead do is think about having what I'm showing on the bottom right here, where we have two layers, and one layer absorbs the low energy red light, and the second layer absorbs the high energy blue and green light. And you actually are able then to keep more of the high energy in your electrical circuit. The issue is that you're not able to build this kind of design with silicon alone. So you actually need a second material. And one of the most promising materials for that second material is a material class called halide perovskites, which were discovered 11, or shown to be good for solar panels about 11 or 12 years ago. Since then, there's been a huge amount of progress experimentally, but there's been less sort of standing back and assessing how far we can actually get, which is what we wanted to do here. So sorry, just for the avoidance of confusion, this design in the bottom right is called a tandem. So that's what I'm referring to here. And to work out how good a tandem halide perovskite solar panel can be, we just need to fundamentally measure two things. We need to measure how much light the material can absorb, and also how well it can hold that energy once it's absorbed the energy. So we went into the lab with state-of-the-art halide perovskites, and to measure the absorption, it's a very easy experiment fundamentally. You just count the number of photons hitting the material and the number of photons not being absorbed by the material. And from that, you can get out something that looks quite complicated like this at first glance. But if you look at this black line, basically you absorb no light. And then there's this sort of turn on here. So above about 1.7 electron volts, which in English means red light. So for red light upwards, you start to absorb quite a lot of photons. And what this experiment allows me to do is not only work out how much this specific material absorbs, but from that I can then calculate how much different thicknesses of the same material will absorb. To measure recombination, I won't go into that in much detail, but effectively we're measuring how long energy lasts within the material. And the way we do that is we fire short laser pulses at the material, and then we time how long energy lasts in the material following those short pulses. We get something like this coming out that I won't go into in any detail. Effectively, this is the number of electrons in the material on the bottom, and then this is how quickly the electrons are being lost on the y-axis. If I put all that together, then I can come out with this figure quite readily that the limiting efficiency of a halide perovskite is 41%. And if what I'm showing here is the limiting efficiency as I vary the thickness of this red and green layer, the low bandgap and the high bandgap layer. And you can see that to get this 41%, you've got to be very specific with your design criteria. You have to be in this very small region of thicknesses, which is quite tricky to do experimentally. At this point, we actually, because of another work we were doing at the same time, thought, hang on, there's another process we could include in our modeling, which is light actually being re-emitted from one material and then reabsorbed in the other material. And this normally is not included in simulations, but is a physical process that always happens. And when we included that in simulations, we were really surprised because we came out with this graph on the right. And if you compare it to the left, you can see that actually suddenly you can make a very high efficiency halide perovskite tandem with a huge range of thicknesses. The slight downside is the limiting efficiency falls ever so slightly to 40.8%. But this right-hand side graph shows that, yeah, it's much easier to make this kind of tandem than previously understood. Everything I've shown thus far is on totally idealized systems, so perfectly reasonable criticism is, what about realistic solar cells? So we can take our models a bit further by thinking about that. And so here we model that by including what's called trapping rates. So on the previous slide, I was effectively showing the results with no trapping, which is an ideal solar cell, which is in the bottom left corner of this plot. And this cross here marks where we're currently at with halide perovskite materials. So with the materials you can make today, you could make a tandem solar panel that's about 33% efficient. So yeah, there's still actually quite a way to go in terms of improving how we make these materials before we can get to this absolute top efficiency. And lastly, we were just able to find sort of luminescence coupling starts to play a role when I'll rephrase that. We're just at the cusp of where luminescence coupling will start to play a role. So this cross again marks where we're currently at, and this sort of red region at the bottom is where luminescence coupling will be important. So we're just getting into that region. Everything I've shown here pretty much is simulation results. Obviously, you want to show that what you've predicted occurs in reality. So the last thing we did in this study was we took an actual halide perovskite tandem and we shone laser light on this green layer. And then we were able to shine laser light on the green layer, the high band gap layer, and then observe emission from the low band gap layer. And we were able to show that there's light going in, being transferred across, and then coming out, which is this process of luminescence coupling that we found was surprisingly important in these materials. So just to sum up, yeah, the next generation of solar panels is has a limiting efficiency much higher than silicon solar panels that you can currently buy. And we're already progressing well towards that limit. Luminescence coupling means it's actually easier to make these new solar panels than has been previously understood. And we've showed that occurs in experiments. A couple of people are probably wondering why I haven't discussed silicon and halide perovskite mixed or something like that. We also did that analysis, but slightly too much to talk about just now. So I'll just refer you to the paper for that. Now, I'd just like to thank all the people who helped with that, my funding, and everyone watching for their attention, and happy to take any questions. Thank you.
Thanks very much, Alan. Brilliant. We've got quite a few questions in the chat. We've got one from Eric, which maybe if I'm allowed, I can maybe develop a little bit. Where are we in terms of commercialization and scale up, and how soon will they be available for general use? My question was going to be, is this possible? Are these luminescence coupled tandems possible roll to roll, and is that the sort of thing you could envision happening commercially everywhere?
Yeah, so I'm not up to date. The last time I looked at this was about 6 months ago. Currently, they were saying the first commercially sold tandems with some amount of halide perovskite in, so that's slightly more halide perovskite and silicon mixed, is the start of next year. There's a pilot plant in Germany that is just starting work now. That's a company called Oxford PV doing that. There's a number of others around the world. I would say all halide perovskites, we're probably talking 2026 to see sort of start of market penetration, but of course, depends who you ask with any of these things too. So I think, yeah, certainly by the end of the decade, there's potential for start to scale up to a significant amount.
Okay, fantastic. I've got a quick question about the interface between the silicon and the perovskite. Does the like the alloy concentration affect how the interface works? Like, what does it affect the coupling, and do you lose a lot of photons, or sorry, do you lose carriers at that point?
Yes, you can do. So just to, for the avoidance of confusion, most of that talk was about all perovskite, but then you still have an interface between the two. You can also have silicon and perovskite. In both cases, the interface between the two is really the tricky bit to optimize, and it's also the bit we probably have the least understanding of what's actually happening physically. And it's a lot more guesswork there, if I'm totally honest. But yeah, people are moving forwards on that quite rapidly at the moment.
Okay, brilliant. Thanks very much, Alan. Great talk. If we move on to our next early career speaker, we've got Emily Bugden. Emily works on climate change and sustainable finance at the Centre for the Study of Existential Risk. And her talk, very cool talk title, Benchmarking the Benchmarkers. Thanks, Emily.
Thanks so much. Can you see that all right?
Yep.
Okay, great. My name's Emily. It's great to be on the call. I'm a visiting researcher at the Centre for the Study of Existential Risk, working on sustainable finance. And today I'll be talking about some of the tools that are being used to measure the alignment of companies and financial institutions with the zero carbon transition. So quite different from the other talks, but we'll see how it goes. So since the Paris Agreement was signed, the finance and corporate sectors have been under increasing pressure to show how they're taking action on climate change. And this has resulted in a lot of companies coming out with commitments for low carbon or zero carbon targets. But there's still many open questions about how to interpret the quality of these commitments. And as an answer to that question, there's been a number of tools that have come out in recent years that are designed to measure the alignment of those targets and commitments. And the tools have become really critical in shaping the trajectory of the transition. So it's really important that they're guiding us in the right direction. But they have a number of kind of common challenges and loopholes that I'm gonna kind of start to address in this talk.
Emily, I think we've lost you. Just see if she makes it back online. While we're waiting for Emily to log back in, if you do have any other questions for some of our previous speakers, you're very welcome to type them into the chat, and they can have a go at answering.
I'm so sorry. Our power just went down and the Wi-Fi went off. Apologies. Let me try that again. Great timing. So the tools that I hope you got up to where I got up to, but these are the tools that are kind of the most prevalent tools in measuring corporate and financial climate alignment. And these are the ones that I have been analyzing. So emissions intensity has emerged as one of the central metrics for measuring corporate climate alignment over the past few years. And there's been an increasing tension between using emissions intensity and using absolute emissions as whether it's the most effective way to measure a company's climate progress. The emissions intensity metric rose to popularity through a project launch in 2014 by CDP, the World Resources Institute, and WWF, who developed a methodology called the sectoral decarbonization approach, which kind of develops a metric for emissions intensity that measures the emissions of a company as a product of total activity. So the graph shows the emissions intensity of electricity sectors in a number of countries. And the emissions intensity target for each sector is defined by calculating a carbon budget based on scenarios developed by the International Energy Agency. So this sector-based emissions intensity approach has become foundational to many of the corporate climate alignment tools, including the Transition Pathway Initiative, the Science Based Targets Initiative, the Climate Action 100 Benchmark, the Paris Agreement Capital Transition Initiative, the Partnership for Carbon Accounting Financials, and the TCFD Knowledge Hub. And it's also formed the basis of an increasing number of corporate climate targets for high carbon companies such as BP, Shell, Total, HSBC, and Barclays. So what are the shortcomings and unintended consequences of this? Most importantly, emissions intensity reductions don't always result in real emissions reductions. So in the graph below, you can see analysis done by Oil Change International of Shell's 2017 climate target of a 50% reductions in emissions intensity by 2050. The pale gray section shows the reductions in emissions intensity, and the dark gray shows that if Shell will continue to pursue a growth strategy, which is its current plan, the real or absolute emissions could still rise by 10%. Unfortunately, the normalization of emissions intensity has allowed a lot of oil majors to release greenwash climate targets that mask business as usual fossil fuel expansion plans or unrealistic reliance on greenhouse gas removals. Additionally, an additional problem with emissions intensity is that it doesn't recognize or incentivize wind down strategies, or managed decline, it's sometimes called, which is where a fossil fuel company chooses not to transition or to diversify into alternative energy sources and instead gradually close its assets and return capital to shareholders. But since a very few companies will really be able to make this transition, it's important to recognize and reward wind down approaches. Emissions intensity metrics can also enable unrealistic assumptions about offsets and negative emissions technologies without a great deal of transparency. So some argue that offsets act as permission to pollute, which can slow down companies taking real action to reduce their emissions, or what we've already heard about some of the more fundamental changes that we need to take today. But this has been termed mitigation deterrence. In other cases, it's just masking very unrealistic assumptions about offsets. So Shell's latest 1.5 degree climate pathway is almost identical to its 2 degree pathway, but it now includes plans to plant a new forest over an area the size of Brazil. And if their climate targets went ahead as planned, 2 companies, Eni and International Airlines Group, would use up 12% of the world's total nature-based offsetting capacity alone. So clearly that's not realistic. But because emissions intensity metrics net out on sustainable activities against emissions often, this means that corporate targets can look more ambitious than they are. But what matters for the Earth's atmosphere is the total concentration of carbon. So for this reason, a number of organizers, academics, and activists have been calling for an end to including offsets in corporate climate methodologies. It's important to also note that offset projects have been involved in a number of high-profile scandals where they've turned out not to exist at all, or they've been involved in biodiversity destruction land grabs, and even assassinations. So there's justice implications as well. The sectoral decarbonization approach methodology also acknowledges these challenges, and it says that absolute emissions reduction targets are the most effective in reducing global atmospheric emissions. So why has emissions intensity become so widespread? The most commonly cited reasons are for companies making it easier to set achievable targets, and for investors making the companies comparable between sectors, or sorry, within sectors. And this is the kind of sectoral decarbonization approach's justification for emissions intensity methodology, which is that targets may be more challenging to achieve if a company is growing. In other words, it's the ability to insert these tools into the current paradigm of corporate relations without disrupting norms around growth or comparability, and that's been seen as a more legitimate way to drive change than setting targets that might be more effective in driving real emissions reductions. What matters in terms of climate impacts, however, is the level of absolute emissions that are released into the atmosphere. The higher the level of emissions, the higher the risk of adverse impacts. Precise estimates vary, but there's agreement that a large quantity of existing reserves need to remain unburned to achieve the Paris goals. Some studies estimate up to 80% of fossil fuel reserves are unburnable, and the UN Production Gap Report released annually estimates that by 2030, on current trajectories, we will have produced more than double the quantity of fossil fuels that can be burned in order to remain within below 2-degree carbon budget. So what do we need? We urgently need tools that drive real world emissions as a priority, rather than making it easier for corporates to set targets that they find achievable. Though I focus on emissions intensity here, there are a number of issues that kind of limit ambition for these tools. And in particular, the qualities of the targets that we need are, we need targets that focus on driving at real emissions reductions without relying on offsets or negative emissions technologies that aren't always proven. We need targets that take a fair account of a fair share of emissions for richer companies and countries that have a responsibility for producing more historical emissions. We need targets that take account of the full scope of greenhouse gases, scope 3 emissions and all owned emissions. We need short, medium, and long-term targets to 2050. And we need targets that benchmark against low-risk 1.5 compatible scenarios. Thanks very much.
Thanks very much, Emily. Fantastic talk. We've got a question in the chat from Jonathan Cullen. So Jonathan recently had an AC company arguing that zero carbon meant zero change to their carbon footprint rather than reduction to absolute zero carbon. Are you seeing this type of blatant misleading?
I have to say I haven't seen anything that egregious. Tends to be that companies are more claiming that their plans are compatible with a zero carbon transition, but when you dig into the detail, you find a lot of loopholes. I haven't seen anyone making that argument in particular, but you will often see other issues like, in particular, the way corporates draw their boundaries. So BP's recent climate targets exclude its large stake in Russian oil company Rosneft, which is an equity stake, so not a controlling stake, but that represented more than 40% of its emissions in 2019. So you kind of really need to dig out into the detail on these commitments, and there's not much capacity to do that on an individual company basis. So that's why these tools are so important.
Okay, and we've got another question from Eric. Today is Finance Day at COP26. Are you optimistic about what commitments, tools and announcements may come out today? And what would you like to see? What is realistic?
Yeah, I think so. The methodologies for measuring financial institutions' corporate climate targets are much more nascent than for other sectors. So you've seen a lot of kind of limited ambition in this area. So net zero targets that only cover 70% of portfolios, excluding motor loans and mortgage loans, which are, as we've heard today, are kind of some of the most critical sources of emissions, especially in the UK. And so I think I'm not optimistic is the answer to that question. However, in terms of what I'd like to see, I think it's really important that we start to require these companies to produce targets that cover the full scope of their activity, and that includes kind of, the full scope of their corporate boundaries, their equity share ownership, and also making targets that, like I mentioned in the last slide, account for their fair share. So you often find corporate climate targets will aim for 45% reductions by 2030, which is what the IPCC has said is the minimum to achieve 1.5. But these are companies that have profited for sometimes a century from, releasing large quantities of emissions. And I'd really like to see higher levels of ambition from those companies. So like 60, 70% targets emissions reductions by 2030. And I think we have to start expecting that from ourselves as well as from them. Let me see a few other questions. Do you want me to read them out?
Can I just ask the one from Keshav? Would you still be against offsets if they were priced high, so that they could only be used for absolutely unavoidable emissions?
Yeah, I think I am on the university's offsetting working group, so I'm not against offsets overall. It's just, I think for the corporate sector, they have been so egregiously used for greenwashing that I have real trouble allowing them to be used and integrated into the at least emissions reduction plans to 2030, where we should be making those reductions that are sort of the easiest, and especially for sectors where there are quite clear technology alternatives. So I think at least in the short term to 2030, I don't see it as valuable to include offsets in emissions reduction plans, because I think you kind of run into these issues around mitigation deterrence that I've covered. And there are a number of examples of this in the sector, like Shell was able to generate credits from reducing its routine methane flaring, which should have been doing anyway. Then it sold the methane, which was burned elsewhere in its supply chain, and it made money out of it. So it's kind of like troubling to think about the inclusion of offsets in these climate plans, especially because of these kind of justice and equity issues that are so widespread in the sector. So I don't see a useful role for including them in especially the oil and gas and utility sectors.
Okay, brilliant. And thanks very much, Emily, for some real fantastic insight into this. I didn't realise that it was such a difficult field. If you don't mind having a quick look through the chat just to see if there are any questions, we can move on to our next speaker, Christos Vlachakis from the Department of Engineering in the Geotechnical and Environmental Research Group, and his title is Mitigating Carbon Emissions by 3D Printing Alternative Cements.
See my screen? Hopefully, yes.
Yeah.
Okay, cool, thanks. Hi everyone, my name is Christos Vlachakis, and I'll be giving you a presentation on mitigating carbon emissions by 3D printing alternative cements. So something that came up in most of the previous talks is concrete. So concrete is the most widely used material in the construction sector. And unfortunately, it amounts to about 8% of global carbon emissions per year. Now, the thing is, one thing we have to ask is, why does concrete actually amount to so much carbon emissions per year? And the main reason is due to Portland cement. Now, Portland cement is actually the main constituent of the concrete that we use in the construction sector. Portland cement, yeah. So Portland cement is made through the process here that's outlined on the figure on the right. So not to go into too much detail, pretty much in order to make cement, we need to burn fossil fuel and reach very high temperatures at about 1400 degrees Celsius. And during this combustion process, we release carbon dioxide and some other gases such as calcium oxide into the atmosphere that all contribute to greenhouse gas emissions. So one thing we need to ask ourselves is, can we just use a more environmentally friendly type of cement? And there are quite a few options out there. One option is alternative cement. So basically, we can use supplementary cementitious materials to produce alternative cement. So things that would have been in smaller quantities in previous types of mixes, now the smaller quantities are actually the main constituent in our building material. And this work, pretty much what we focused on was actually calcined clays. Instead of mixing it with water, we actually activated it with alkaline solutions that are rich in sodium or potassium. So, and these binders are also referred to as geopolymers. So basically, if we opt for geopolymers, we can actually reduce the embodied carbon in structures up to 80% if we compare it to conventional structures that would have used Portland cement. Now, one of the things is why should we focus on geopolymers? The thing is, geopolymers, apart from being an alternative cement, they're also multifunctional materials. As we mentioned before, we do need an alkaline solution to make them that is either rich in sodium or potassium. Now, these alkaline ions, their presence actually allow geopolymers to be a multifunctional material and actually be used in structural health monitoring. In simple terms, we can, apart from using it as a structural bearing material, we can also use it as a sensing material. And the way that it would be used as a sensing material is quite straightforward, actually. So what we need to do is pretty much just be able to extract a resistance value from our material right here, and then overall just examine and see how does that resistance value change. So pretty much we want to see the fractional change in the resistance compared to external stimulants such as strain and temperature. Now, having all this in mind, something else we need to ask ourselves is, how can we actually apply this thing? So we obviously have like the techniques of manual application as well, but we want to consider something a bit more novel, a bit more different. And something we can do is actually with the use of robotics and 3D printing. So 3D printing is a layer by layer process that actually involves the extrusion of, in this case, cementitious materials without the use of any formwork. And the reason why we want to use 3D printing is, first and foremost, is because it's able to reduce construction waste and minimize carbon footprint. So pretty much we're not going to have all that waste that is usually associated with all that, like at all those construction sites that we would normally see. Secondly, and also very important, is that it allows for flexible design. So basically with conventional molds and formwork, we're not able to achieve some weird and unique shapes. With 3D printing, since we don't have any formwork at all, we don't need any extra material. So again, this contributes to reducing all that waste and minimizing carbon footprint. And some additional features of 3D printing: it's a repeatable process. We're able to achieve the same result throughout all processes. It has fixed costs, and lastly, it can also be used in inaccessible environments if we're looking at on-site, like on-site applications, pretty much somewhere where it wouldn't be that safer to actually send someone to go. Now, what we see here is just a very basic 3D printing setup. We have a dispenser mounted onto an XY gantry of a 3D printer, and this allows us to print the activated calcined clays that we mentioned earlier. We're able to achieve some rectangular blocks right here. Something else we can do is we can also print directly onto concrete elements. So basically on the left-hand side here, we just see that coating that's being applied onto concrete slab. And on the right-hand side, similarly, we have a coating that's being applied onto reinforced concrete beam. So taking all this into account, essentially what we want to do is we want to 3D print geopolymer sensors for concrete infrastructure. In order to do that, we'll just have to break this topic down into 3 simpler subtopics, let's say. One is how do we 3D print geopolymers? Next thing is what is our strain and temperature response of the geopolymer materials? And thirdly, we have to also assess the bond strength, because we'll be applying these sensors on top of existing infrastructure. And since we'll be doing 3D printing, we can assume some sort of difference in mechanical properties. To start off with 3D printing geopolymers, again, I don't want to get too technical. We have to look at some additional properties. These are extrudability, open time, and buildability. In essence, what these properties do is that they just answer these 3 questions. Extrudability, can we actually extrude the material? Open time is how long can we actually extrude it for? And buildability, how many layers can we safely print? So in this situation, we were able to actually extrude the material for 120 minutes, so 2 hours, at a reasonable consistency. And we're able to print it for 10 layers without any noticeable deformation. So that was actually quite higher than the requirements of this study. So pretty much once we have satisfied all those requirements, we're able just to print a patch onto a concrete cube, as I mentioned earlier. And the next thing we do would be actually to assess the sensing side of things. In particular, look at geopolymers as strain sensors. So what we have here, there are basically 2 basic modes of load, compression and tension. In regards to compression, what we have is that once we apply load, the resistance of the material actually decreases, and in tension, the resistance of the material increases, as we see here. And the reason for that is, firstly, under compression, once we actually apply the load and we squeeze the material, let's say, the distances that the ions actually need to move become smaller, and therefore this leads to reduced resistance. In regards to tension, similarly, since we're stretching it, the distances that the ions need to move is actually increased, and therefore this leads to increased resistance. And by assessing the sensing capacity under compression tension, we're also able to extract the gauge factor in each situation, which is about 10 for compression and which was about 14 for tension. Moving on from strain, we can also use these materials as temperature sensors as well. So basically, we have 2 graphs here. They're fairly basic. We're essentially measuring the resistance at different temperatures, 10, 15, 20, 25, and 30. And then we're also characterizing the change in temperature, which is, in this case, an exponential fit, which could also be, it is also sometimes characterized as a second degree equation as well. Something you probably already noticed is that once the temperature actually starts increasing, so we go from 10 to 15 to 20, 25, and 30, the resistance of the material actually decreases. And the reason for that is due to increased ion mobility. So basically what this means is, as the temperature increases, the ions pretty much move faster, and the faster they move, the lower the resistance. And likewise, the opposite occurs. The lower the temperature, the slower the ions move, and therefore the higher the resistance will be. And lastly, we also need to look at these coatings in terms of adhesion. Pretty much, since it is a additive manufacturing process, the mechanical properties are going to differ than what we would have had in a manual application. Right now, we're at about 0.7, 0.8 megapascal, which is a serviceable, limit, but we can always achieve higher strength in that aspect. Yep. So to conclude, just some of what we talked about, geopolymers are alternative cements that can be used to reduce the embodied carbon of structures. 3D printing provides flexibility in the fabrication of binders and can allow us to reduce construction waste. And thirdly, compared to other alternative cements, geopolymers are multifunctional materials, and they can be used for structural health monitoring and allow us to take preemptive actions in any sort of things that might occur in our structures. I'd like to thank you for your attention. Please ask any questions.
Thanks very much, Christos. Fantastic talk. Please do put your questions in the chat. We've got one here from Eric. He is asking, in terms of buildability, what size and type of structure are you safely able to build with these geopolymers? And do you think one day whole buildings could be built using this material?
Okay, so start off with the size and type of structure. So since we're looking at coatings, the buildability requirements aren't very high. So in this situation, we're looking at 2 to 3 layers. So we're looking at, let's say, just a few millimeters thick in this application. So we're looking more of, let's say, it's a non-structural coating, but in some cases you can even characterize it as just a decorative coating. So we're not looking so much into it's going to provide any, let's say, protection. It's more of just going to act more as a sensor. And in terms of whole buildings be built with geopolymers, as far as I'm aware, there are actually buildings that have been built with the geopolymers. I know for some cases in Australia, I think an airport in Australia actually used geopolymers to for some construction sites. So the thing with geopolymers is that it's not so much a concept anymore. It's more of something that's it's not just an idea. It's something that's actually being implemented. It's so I think the main issue with geopolymers is that it just needs to be used more, pretty much, to get out there rather than actually just sticking to the lab, let's say.
Okay, fantastic. If there are no more questions for Christos in the chat, I would just like to thank all of our speakers, our keynote speakers, James Woodcock, Ian Parry and Jonathan Cullen, and our early career speakers, Alan Bowman, Emily Bugden and Christos Vlachakis. And I'd like to thank the audience as well for coming and contributing to the chat and asking questions. And please do go to the Cambridge Zero website for information about the upcoming research symposia